So today one of the things we're going to look at here is analyzing graphs of functions. So we're going to take a look at some different things with domain and range. We're going to take a look at what's known as the vertical line test. And we're also going to take a look at some different things involving how you find what's called the zeros of a function, which are, graphically speaking, how to find x-intercepts algebraically. So when we're talking about the graph of a function, we're going to first look at some different things involving the domain of a function, set of all possible x values, and we're going to take a look at the range of a function, set of all possible y values, and we're going to do that mostly through looking at graphs. So here's an example of a domain and range type question of a function when we're talking about analyzing a graph. So we're going to use this graph to answer each of these questions here. So part A first asks, what's the domain of f? So what we're looking for here is, what are all the possible x values that you could use from this graph right here? So I'm basically using this graph to answer these questions here. So when we're looking at the domain of a graph, what we're basically looking for here is a range of values along the x-axis, and we're going to read this graph from left to right. So what I'm looking for here is, where does the graph start on the left? Where does the graph finish on the right? So I think you can see here, this graph starts along the x-axis at -1, and then is going to travel to the right all the way to +5. So what we would say the domain for this is, and there's two different ways that we could write this. We could say that the domain of this is from -1 to +5. But notice the points that we have on the graph here. This closed circle here, if you remember some different things that you did in the past with greater than, less than, that means equal to. This open circle here that you have on the end of the graph, okay, that means up to and including, but not equal to. So the -1 value for x is included in the domain here, but the value of 5 is not. So that's why I have equal to here, but only less than here. So another way to write your answer to something like this is to use what's called interval notation. So interval notation is a way to basically take this expression here and just make it in a little bit more simple terms. So if I was to write this in what's called interval notation, what I would basically do is this. I would have parentheses, -1, comma, I'm sorry, let me back that up. That shouldn't be a parentheses, that should actually be a bracket. So let me erase this here. So I have a bracket around the -1, and I just have a parentheses around the 5. And so what this is it's another way of writing what the possible values of x could be here in what's called interval notation. A bracket represents equal to, parentheses just represents greater than, less than, but not equal to. So that's why I have a bracket for the equal to part, but just a parentheses for the less than part here. So that's the domain. So we're basically looking at the graph from left to right. So the second part of this, the function value. So what we're basically looking for here is, for this here, if I put a -1 in for x, or if I go to -1 on the x-axis, what would be the y value of the point there? So as you can see here, you have the coordinates for this point. So f of -1 here would be +1, because that's what the corresponding y value is when x is -1. And then if I go to f of 2, meaning what is the y value when x is 2? So here's where x is 2, here's the point that corresponds to that, here's the coordinates for that point. So we would say f of 2 equals -3. So that's what I'm looking to do when we're talking about functional notation and function values within a graph there. And then for part C, the range of f. So remember, range is the set of all possible y values. So with domain, we were reading the graph from left to right. With range, we want to read it from bottom to top. So I want to do that right there. So I'm basically looking at the range as, at what point on the y-axis does it start down here, and then where does it finish up here. So the range from this graph goes from -3 all the way up to +3. So we could say this, if we were going to use inequality signs, we would say -3 less than or equal to y less than or equal to +3. Or I could say bracket -3, 3 bracket. Like I said, brackets are another way of saying equal to. So notice I'm doing equal to's here because both of these points are filled in circles, which means it's equal to, which is different than what we said about this open circle, which means not equal to. So that's just some different things involving domain and range with a graph. So one of the things that we've looked at previously was the whole business of when you have a relation, how do you know if it's a function? So we talked before about how you algebraically know if you have an equation, how do you know if that equation is a function. But if you have a graph, how do you do that? So the vertical line test is what you can use when you have a graph and you want to know if that graph, if that relation is in fact a function. So if you have a graph or a set of points in a coordinate plane, we say that y is a function of x if and only if no vertical line intersects the graph at more than one point. So if you have a graph and you draw a vertical line, remember that's a line that goes straight up and down. If you draw a vertical line anywhere on the graph and that vertical line passes through the graph in more than one point, then we would say that that graph is not a function. So here's just some examples here that we're going to use the vertical line test for. So you have part A here, and I drew your vertical lines here. So for part A, notice this would be not a function, because I drew a vertical line. As you can see here, this vertical line goes through more than one point on the graph. And there are other places you could draw vertical lines where that would occur, but that is what makes this not a function. For example 2, I drew my vertical line here. So regardless with part B here, regardless of where you draw your vertical line, it's only going to cross the graph in one place. So we would say, yes, this one is a function. And for part C, notice I drew a vertical line. This is what's known as a piecewise graph because you have two different pieces here that are kind of broken up. But once again, no matter where I would draw the vertical line here, that vertical line would only cross the graph in one place. So we would also say that this is a function. It's a piecewise function, but still a function nonetheless. So that's just a real quick and easy way when you have a graph, if you can determine if the graph is a function or not. So some other things that we're going to look at as far as analyzing graphs has to do with zeros of a function. So the way you find the zeros of a function are you take an equation, you set it equal to 0, and you solve the equation for x. So the zeros of a function, graphically speaking, are the x-intercepts on a graph. So one of the more important things that we look to find when we're analyzing a graph, if we have an equation and we're trying to figure out what the graph looks like, one of the more important things to find out is what the zeros of the function are. What are the x-intercepts of the function? So here's an example, and the question asks you to find the zeros. So I got this here. I got 3x squared plus x minus 10 equals 0. So once again, because it's a quadratic, I want to attempt to factor this. So I got this here. So I got 3x, I got x here, and then notice with this you have 10, you got 2 times 5, right? You got 1 times 10. I'm going to try 2 and 5 first, since that's the pair that's closest together. So when I put the values in here, I'm going to put the 2 here, I'm going to put the 5 here. And notice because it's a negative 10, the signs have to be different. So I'm going to put because it's positive in the middle, I'm going to put the plus here, and I'm going to put the minus here. So when I go to check this, right, I got 3x times positive 2, that's positive 6x. I'm just going to kind of put this over here. And then when I go to do this, negative 5 times x would be negative 5x. And when I put that together, I get positive x, okay, which is what's in the middle here. So I know that I factored that the right way. So now all I want to do is just take each of these, and I want to set them equal to 0. And I want to solve each of these. So To solve this first one, I'm going to add 5 to both sides, and then I'm going to divide by 3, and I get x equals 5/3. This equation here, I'm going to minus 2 on both sides, and I get x is -2. So there's the second solution there. So just real quick, let's go through just once again how you use your calculator to check your answer to something like this. So what I want to do here is I'm going to do the whole storing number thing in my calculator to figure out if in fact these answers are correct. So let me kind of exit out of here and come to this here. So first I'll try 5/3. So I'm going to do 5/3. So remember that's just 5 divided by 3, store x. And then I'm going to type in the equation. 3x squared plus x minus 10. Get an answer. Make sure it's 0. Then I'm going to store -2 in for x and see if I get the same thing. So I got -2, store x, and then I'm going to put the equation back in and just make sure when I do that, just make sure it equals 0. So once again, just something you can do with your equations there to check to see if what you did was right. So that's part A. Part B, same thing. I'm going to take the equation, I'm going to set it equal to 0. So I have the square root of 10 minus x squared equals 0. So the first thing I want to do here is I want to square both sides. That'll get rid of the square root. And the nice thing about that is when I square 0, it's still 0. So I end up with this, 10 minus x squared equals 0. So from here, the easiest thing to do here is just to add x squared to both sides. So I end up with this, 10 equals x squared. And then I'm going to square root both sides at the end. So when I do that, I get x equals plus or minus, right? Remember, we're square rooting both sides, so it's got to be plus or minus. So I end up with x equals plus or minus the square root of 10. So that would be the zeros there for part B. For part C, same thing. I'm going to take the equation here. I'm going to set it equal to 0. So two things to remember here. One is, if you're not sure what to do, you can always take this, put it over 1, and cross multiply. That always works. But the easier way to do this would be to take the numerator and set it equal to 0. And the reason for that is because when the numerator of a fraction equals 0, that makes the entire thing equal 0. So anytime you have a fraction set equal to 0, all you really have to do is just take the numerator and set it equal to 0. So to solve this, I'm going to add 3 to both sides, divide by 2, right, and I get 3/2. Okay, and that's the 0 for part C. For part D, notice you have a value here that has a degree of 5. So what I want to attempt to do here is I want to attempt to factor this first. And I know that we're used to seeing this first term as being x squared, but this time it's x to the 5th. But the way I'm going to factor this is very similar to what I did as if it were an x squared in the front. So remember that when it's x squared in the front, we put x's in the front of the parentheses because x times x is x squared. So if I tried to break up x to the 5th, I could do that in a number of ways. I could say x to the 4th times x. Right? I could say x cubed and x squared. And what I want to do in terms of which of these two am I going to go with in the front of the parentheses, take a look at what's in the middle. And if you notice in the middle I have x to the 4th, x to the 1st. So I'm going to do this in the front of the parentheses first. I'm going to go x to the 4th times x. And I'm doing that because that's what I have in the middle. I got x to the 4th in the middle, I got x to the 1st in the middle. Then notice here at the end it's -2. So because of that, the signs are going to be different. So I'm going to have for this just 1 times 2. That's my only possibilities for the numbers that go in the back. So just notice with what's in the middle. The -2 is with the x to the 4th. The +1 is with the x. So I'm going to do this. I'm going to do this. Then I'm going to check it and see if it works. So when I do this, x to the fourth times negative 2, that's negative 2x to the fourth, which you can see is the same as this here. And then I got 1 times x, which is just x, which is the same as this here. So that has been factored. Now I just want to take each part and I'm going to set it equal to 0. So I end up with this. So when I solve this over here, I got x to the fourth equals negative 1. And then I would take the fourth root on both sides. So this will be x equals, now I'm going to do plus or minus again here because this is an even value here. So I'm going to have plus or minus just like I did with x squared. So this would be the fourth root of negative 1, which is going to get me an imaginary solution there. And then I have with this over here, I'm going to add 2 to both sides, and I get x equals 2. So one of the things I just want to point out to you about this, and that is when you go to check this, or when you go to graph this, just notice that because there's only one real solution to this, so let me pull this up here. So this is x to the fifth minus 2x to the fourth plus x minus 2. So when I graph this, just notice with this, the graph is only going to cross the x-axis one time, and that's going to be at positive 2. So even though it's x to the fifth, there's 5 zeros here, only one of them is real, and that's why this graph only crosses the x-axis in one spot. So just something I just wanted to kind of point out to you, because that's going to be significant for some things that you'll see down the road here. So going to the last part of this, and this is x cubed minus x squared minus 30x equals 0. So hopefully you notice here that each one of these terms has an x. So let me factor that out first. And when I do that, I get this. X squared minus x minus 30 equals 0. Then I want to take x squared minus x minus 30, and I want to factor that. So I'm going to leave that x in the front. So this will be x times x, and this will be minus 6 plus 5 equals 0. Now I just want to take each of these parts and set them equal to 0. So I got this here, x equals 0, right? Then I got this here, x minus 6 equals 0. And then I have this here, x plus 5 equals 0. This one's already solved, so that's nice there. This one here, I'm going to add 6 to both sides. I get x equals 6. This one here, I'm going to minus 5 on both sides, and I get x equals negative 5. So those are the 3 zeros that that equation has. So that's a very, very, very important thing when we're looking at analyzing graphs. We want to know what are the zeros of the function. And when you have zeros that are real, those real zeros, graphically speaking, represent x-intercepts. So the last thing I just wanted to look at with you for this was what's known as increasing functions and decreasing functions. So one of the things that we look at with a graph is how the graph behaves as we read it from left to right. So similar to how we were talking about with lines and slope, how you read, just like you read a line, just like you read a book, you read it from left to right. Any graph that we're going to look at here, we're also going to read from left to right. So this is, I think, a very good illustration in terms of what we're sort of looking at when we look at increasing, decreasing versus constant. So here's just a graph. Just notice it has a starting point, it has an ending point here because we're going to read this from left to right. Notice the graph starts out in a decreasing type of nature. It's moving in a downwards direction as I read it from left to right. Then it becomes constant. It becomes flat when it gets to this point here. Once again, still reading it from left to right, and then once I get to this point here, it begins to increase as I read it from left to right. So that's one of the things that we're going to look at in terms of if you have a graph, okay, what interval along the x-axis is the graph increasing, what interval is it decreasing, what interval is it constant along. So for this particular graph, we would say that this graph is decreasing from -2 to 0, and then it's constant from 0 to +2, and then it's increasing from +2 to +4. And all we're doing is we're just reading along the x-axis how the graph is behaving as we kind of go through there. So here's an example. Got part A. So keep in mind with these graphs have arrows on the ends of them. I know they're not on here, but you might want to fill those in. Okay, like this here. So with this particular graph for part A, notice that you have, this is the equation y equals x cubed. So the graph starts down here and it makes its way up, it comes over, okay, and then it comes up here. So this graph is increasing the entire time as I read it from left to right. I know this piece in here looks like it's kind of flat, and that's a common mistake that people make when they look at the cubic. The cubic graph is always increasing. So even though this looks kind of flat in here, it's not. It's just increasing at a much, much slower rate than the ends of the graph are. So what we would say about this graph is this graph is only increasing, and whoops, wait a minute. This graph is increasing from -infinity to +infinity. So if you recall how to do the symbols for that, we would say that this graph is increasing from -infinity to +infinity. Because this graph has arrows on the ends, this graph is going to go infinitely in the negative direction, this way, and it's going to go infinitely this way. Now part B is a little bit different because the graph is not just increasing the entire time. So once again, I got arrows on the end here. This graph first is increasing, then it's decreasing, and then it's increasing again. So if we just take a look at the first part here, the part where it's increasing. So we would say that this graph is increasing from -infinity, because keep in mind with the arrows on the ends, that means this graph is going infinitely in this direction. And then what happens is as I come in like this, as I'm reading it from left to right, the increase stops right about here. So it stops at -1. Then the graph starts to decrease. And as I continue to go from left to right, the decrease for this will stop right about here, which is at +1. So this graph is decreasing from -1 to +1. And then the graph begins to increase again at +1, and it continues to increase all the way to +infinity. So we would say here that the graph then begins to increase again from 1 to +infinity. So that's just some different things with increasing there. And then the last part of this, part C, just once again, I'm going to just throw some arrows on the ends of this. Okay, this graph, as you read it from left to right, it increases, it's constant, and then it decreases. So I'm just going to make myself some space here. So first, once again, because this graph goes infinitely to the left, we would say that it basically is coming in from -infinity, and the increase for this will stop at 0. Then the graph becomes constant, and the graph is constant from 0 all the way to 2, and then the graph decreases. And this graph decreases from 2 all the way to +infinity. So these values that you're using here are the values along the x-axis. So the last example is this, okay, and you use your graphing calculator to come up with what each of these graphs looks like, and then we're going to do the increasing, decreasing, constant business with this again. So here's the graph for part A, this right here. Okay, and this is just an upside down parabola. So you can see here this graph is increasing, then it hits this point and it begins to decrease. So first I'm going to deal with the increasing part. So this graph is going to remember this has arrows on the end, this graph is going to increase from negative infinity all the way to 0, and then it's going to decrease from 0 to positive infinity. So that's part A. And then part B, once again, it's a cubic, so it has arrows on the ends. So just keep in mind with a cubic, I know this appears to look constant, but it's not. It's just increasing at a very slow rate. So what we would say about this graph is that this graph is increasing from negative infinity to positive infinity. So that's just some different things about how a graph behaves as you read it from left to right, which are some things that are very important with, once again, when you're looking at analyzing graphs. So one of the things that we're going to look at sort of moving forward is we're going to take a look at some different things what are known as relative maximums, relative minimums. We're also going to take a look at some different things involving functions being odd and even, and talk a little bit about some different things that involve with those, some different things involving symmetry again.